Hello and welcome to this video for Chemistry 20, the Solutions unit. This is the second lesson in the Solutions unit where we are going to learn how to prepare a standard solution, and there's two methods that we're going to talk about. So first of all, what is a standard solution? A standard solution is a solution where we know what concentration it has because we've made it to have that specific concentration. We've either dissolved a certain mass of our pure solutes into our solvent, or we are diluting an already made solution that has a higher concentration by adding water to make its concentration decrease to the concentration that we're trying to achieve. So let's look at these two methods. So first of all, if you want to prepare a solution, this is one of the most common ways that we prepare a solution, where we take our solute. Usually the solute is solid because it's an ionic compound, and ionic compounds are always solid. And we need to first, this is kind of like a pre-lab, I wouldn't call this a step, this would be a pre-lab that you have to do, where you have to calculate the mass required to make that solution by being given the concentration and volume. So remember, when you're given the concentration and volume, you can multiply them to find the moles. And from that, you can then find the mass with moles times molar mass. Now you can also convert this into one formula where we have M. We know what N is. N equals C times V, and then we multiply that by molar mass. So it's combining the two formulas together to get mass equals concentration times volume times molar mass. Now remember, your concentration from the last video is in moles per liter. Your volume therefore needs to be in liters, and your molar mass is in grams per mole. So if we were to look at the unit analysis of this, our moles cancel, our liters cancel, and we're left with grams. Okay? So if you are doing it into one combined formula, it's kind of nice because then you don't have to worry about leaving this answer unrounded to put it into the next formula. It does it all for you. Okay? Now, there are 4 steps required to make a standard solution that you need to memorize word for word, these steps. So step 1, you're going to say, I'm going to measure. You don't write this, but this is what you put in the blank. Whatever mass in grams of your, again, whatever the solute is. Write the chemical formula for the solute, and note that the solute, again, is going to be solid because this is before it's being put in water. So it's going to start as a solid most of the time when you have an ionic compound. Now, how we accomplish this in a lab scenario is we take a beaker and we put the beaker on the balance, and then there's a 0 button. You hit the 0 button to make the mass of the beaker negligible. Therefore, when you put your solutes into the beaker, the mass shown is only of the solute. You don't have to subtract the mass of the beaker. Okay? This is a scupula. This is what we use to transfer our solid from either a stock container or a stock bottle into the beaker to collect that mass that you're measuring in order to make your solution. So that is step 1, measure mass of solute. Step 2 is to dissolve the solutes in half the final volume of water, approximately. This is essentially what you're doing is you're making a pre-solution. You're dissolving it so that you can transfer it into something that much more accurately measures volumes. Beakers are only approximate volumes. They don't measure very accurately. Okay, so you're going to, this is called a wash bottle or a distilled water bottle. You're going to use that, squirting water into the beaker. You're also going to have a stir stick. They're little glass rods that you're going to put into the solution to help stir and dissolve your solute. And this, like I said, is just making a pre-solution that we will then put into our volumetric flask in the next step. Okay, so the exact volume you put here does not matter. In a lab setting, don't sit here and try to make it precisely half because the beakers, again, don't measure precise volume anyway. Okay, then in step 3, like I said, you're going to transfer it to a volumetric flask. This is the volumetric flask. It has a bulb on the bottom and a very narrow neck. Now, there is a line partway up the neck that is calibrated for the specific volume of volumetric flask. Volumetric flasks only measure one volume, whatever your final volume is. So you have to say which type of volumetric flask you're going to be using based on your final volume. Can't talk and write at the same time. Okay? So this here, if you can see, is a 100 milliliter volumetric flask. Now this is a funnel. Funnels help us transfer solutions from the beaker into the flask because, again, there's a very narrow opening, so it helps you to do that. So step 3 is to transfer the volume to a final volume volumetric flask. Then your final step actually has 2 parts to it. You're going to first fill it to whatever your final volume is. That information gets put there. And then mix by inverting. So there's little caps that go on top of the flask. They're kind of hard to put on, so don't be afraid to kind of push on there with some force. And then we don't just shake the solution, okay? We invert it. So we turn it upside down and back a couple times, okay? Now, the meniscus. When you're filling a volumetric flask, the water molecules kind of crawl up the side of the glassware, okay? And so you have the line on your volumetric flask. I'll make it purple. That's the full line, the fill mark on the volumetric flask. You want the bottom of the meniscus to be on that line, okay? If you fill it up like so to here, and that's your meniscus, that's not enough volume. You need to be just the line, the bottom of the meniscus right on that line, okay? Now you have to be very careful when you're filling this up because if you go too far, you can't just dump it out and think you're just dumping out water because you're also dumping out some of the solute. So it ruins the experiment and you essentially have to start all over again. Okay, so as you're filling it up the neck, you see the water line come up the neck, go very slowly till you get to that final volume. Okay, so those are your 4 steps: measure, dissolve, transfer, fill, and invert to mix. Let's look at an example. Okay, describe how to prepare a 100 milliliter solution with a concentration of 0.0800 moles per liter. And we are given the formula, so we don't have to write the formula ourselves, balancing ion charges, it's already done for us. Now remember, our units of concentration are moles per liter, so my volume needs to be in liters. So I need to divide by 1,000 to convert it into liters. Okay? To find my molar mass, I have potassium, which is 39.10. I'm going to add that to my manganese. That's not magnesium, that's manganese. I just need to grab my periodic table because that's not a common one. Manganese is 54.94, and I'm adding that to 4 oxygens, which are 16.00. Okay? So find your molar mass in one step in your calculator using this approach. 39.10 plus 54.94 plus 4 in brackets 16.00. We get a molar mass of 158.04 grams per mole for our potassium permanganate. Okay, so this was our volume again when I divide by 1,000. This is my concentration. So now again, if I do my calculation in one step, concentration times volume times molar mass, I will have my concentration of 0.0800 moles per liter. So it's mole over liter. I only write this division symbol again to show my units for unit analysis. There's no numbers down there. It's just for unit analysis, which is important in chemistry to make sure you have your answer in the proper units. Okay, so my volume in liters is 0.100 liters, and my molar mass is 158.04 grams over mole. Okay, when you have grams per mole and moles per liter, that means that those units are on the bottom. So my liters can cancel because they're on the top and the bottom. My moles can cancel because they're on the top and the bottom. And I'm left with grams on the top. Whatever you're solving for, you should always be left with it on the top. So if I multiply this by 0.1, the molar mass, and the concentration 0.08, I get an answer of 1.2643, so on, grams. Now we still have to follow our sig-dig rules, okay? So I have 3 in my volume, and 3, because leading zeros don't count, in my concentration. So I need 3 sig-digs in my answer. So my final answer will be 1.26 grams, right? I'm cutting it off after the 6. The 4 is not enough to round the 6 up, so it stays at 1.26 grams. Now notice how this question says describe how to prepare. Okay, so what that means is that you're not only calculating the mass, you're then going to write the 4 steps. Okay, measure, dissolve, transfer, fill, and invert to mix. So, and there's more to those things, but that's just how you can summarize it to remember. So I'm going to measure, I'm putting my specific mass, 1.26 grams of, I'm going to put the formula for my solute. So my solute is KMNO4, and again, it's not yet in water, it's in its solid form. Then in step 2, now I dissolve. A lot of students write dilute here. That's not the correct word. Dilute means you already have a solution and you're adding more solvent. We're not doing that. We are dissolving a solid. So we're going to dissolve in whatever half the final volume is of water. It's good to put distilled water, but because technically you should be using distilled water. So half the final volume, our final volume is 100 mils. I'm going to put 50 mils of water in that step. Okay, remember again, it's only approximate. If you put 40 mils or 60 mils, it's fine. Your final volume is 100, so you have lots of play in how much you dissolve it in step 2. But in the procedure, we write half. Okay, then we're going to transfer it. And again, I have to say what size of volumetric flask I'm using, because again, they come calibrated to only 1 volume, so you have to use the correct one. They come in volumes of 100 milliliters, I think actually even 50 milliliters, 100 milliliters, 500, 1,000, 2,000 milliliters, okay? So they come in various volumes. You have to say which one you're using. So whatever our final volume is, which is 100 milliliters, so I'm transferring it to a 100 milliliter volumetric flask. That's what that equipment is called, or that glassware is called, a volumetric flask. Very precise instrument at measuring volume. Okay, and then step 4 is to now fill to the final volume, which is 100 milliliters, and mix by inverting or invert to mix. Same thing. Okay, so mix by inverting or invert to mix. So that is the full procedure on how to prepare a standard solution with a certain mass of your solute. Okay, the 4 steps: measure, dissolve, transfer, fill, and invert to mix. Okay, the next thing we're going to look at is the second way of making the standard solution, which is the dilution. So we're going to talk about dilution and how dilution works. When you have a solution that has a high concentration, we can lower the concentration by adding more solvent. Okay, so if your solvent is water, for example, you're adding more water. Now, it's important to note that what's happening here is the amount of solute I have remains the same. Okay, so for example, let's say I'm starting with a solution and this is my volume and there's 10 moles in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, when I'm talking about concentration, the units are moles per liter. So if I were to look at a 1 liter section, let's say that's a 1 liter section, there's 3 particles in there. So my concentration at that point is 3 moles per liter. Now, if I were to add more solvents, the volume increases of my solvent, but I still have the same number of particles. I still have 10 particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But notice how they've spread out. I have a lot more space there. So they've spread out. So now my concentration, when I'm looking at a 1 liter section, I think a 1 liter section is a millimeter cubed, if I'm correct. Oh, that's I think that's a milliliter. But anyway, when I'm looking at that one little section, I now have 1 mole per liter. Okay? So that section that we're looking at gives us the concentration, but the moles are constant. Okay? So that means that you have the same amount of solute in there. We can talk about, when I dilute a solution, how it affects the appearance. This is a diluted solution of copper. Copper ions are blue in water, and when you dilute it, the color becomes less dark. It becomes less intense because the ions have spread apart, so they're not as close together, making it look less intense. We can also talk about their reactivity. When I want to talk about them reacting with another material, reaction speed is based on collision of particles. So when I have a solution with a higher concentration, the particles are closer, so they are going to collide more with whatever they're reacting with, and therefore the reaction will be quicker. It's not because there's more particles. We've already explained that the particles are the same. You have the same amount of particles when you dilute a solution. Okay? It's just whether they're closer or more spread out. Here they're more spread out. So when they're more spread out, they collide less. And so the reaction will be slower. Okay? That I have a lab with my Chem 20 students that we do where that's a question in the lab, whether their dilute or concentrated solution will react more. And a lot of students put the concentrated one reacts more because there's more particles, but that's not true. The particles are constant, okay? It's just whether they're close together or spread apart. Now, because the moles are constant, that leads us into our formula. Okay, the moles of my initial solution equal the moles of my final solution. And we know that our formula for moles is C times V. So I can write that my C of my initial formula times my V of my initial formula, which is how we solve for Ni, equals C of my final solution times V of my final solution. Okay, so the initial solution is your more concentrated solution. Okay, the one that has a higher concentration. So Ci is going to be greater than Cf. That's the greater than symbol. Okay, whereas our F is the diluted solution. So the diluted solution, because we're adding more solvent to it, Vi is going to be less than Vf because I am adding more solvent, so my final volume is going to be greater. Okay? So my C's again need to be in moles per liter, and my volumes, now in this formula, you can actually have your volumes in milliliters as long as they're both in the same units. Okay? And we commonly deal with small volumes of solutions, so I commonly leave my answer in milliliters. And I'll show you how that works in the question. But if you don't want to remember when can I leave it in millimeters, when can't, always convert it to liters. There's nothing wrong with doing that. Okay? Let's look at a couple of examples. So what volume of a 1 mole per liter solution of NaCl do you need to make a 250 milliliter solution with a 0.2 mole per liter concentration? So this is my initial solution, okay? I'm starting with a higher concentration, so this is Ci, and I am wondering what volume of that solution do I need? This is my final volume, And this is my final concentration because that is my diluted solution. I am making the solution from a concentrated solution. Okay, so you could list your variables again. I'm not going to, just to save time. I'm just going to write my formula. CIVI equals CFVF. I am solving for VI, so I need to divide both sides by CI. Okay, so that means my VI equals my CF, 0.20 moles per liter, times my VF, which is, I'm leaving it in milliliters, and you'll see how this works, divided by my CI, which is 1.0 moles per liter. Now, I kind of kept my units of moles per liter in one line just to show you quickly how they cancel together. So I'm left with milliliters in my final my initial volume, what I'm solving for. Okay, so 0.2 times 250 divided by 1 gives me an answer of 50 milliliters. Okay. If you were to have converted the volume to liters, you would get an answer in liters. It would be 0.05, but you'd need to add a 0 to that to have 2 sig digs liters. So either answer would be fine, unless the question specifies what units it wants your answer in. But again, for sig digs, there's 2 digits here, 2 digits here, because leading zeros don't count, and 3 digits there. So the lowest is 2. So either 50 mils or 0.050 liters. Okay, let's look at a second example. So we are asked, what is the concentration of a solution if it is made? So the one you're making, again, is the final solution. So this is the final concentration that I'm looking for. Okay, it's made by taking 500 milliliters of a 14.8 mole per liter solution of sulfuric acid. So this is my initial solution with the initial volume and the initial concentration. Now, you have to read the questions very carefully. Look what it says. It says that the solution is made by mixing 500 milliliters with 1 liter. You're mixing them together. Okay, so that doesn't mean I'm making it to a final volume of 1 liter. I'm mixing 500 with an additional 1 liter. Okay, now because my volume here, one of them is in liters, I'm going to put them both in liters. I'm going to list them out. Okay, so CF is what we're solving for. VF is 1.50 liters. Okay, because again, my VF is found by mixing my 500 milliliters with 1 liter. Okay, my 500 milliliters would convert into 0.500 liters. So when I add that to my 1 liter, I get 1.5 liters for my final volume. So you have to read the question very carefully. This one says I'm mixing the volumes together. I'm adding them together. Okay? My CI was 14.8. My VI, again, because my VF is in liters, I need to keep this one in liters as well. Or you could put them both in milliliters, as long as they're in the same units. Okay? So my formula, CIVI equals CFVF. I am solving for CF, so I need to divide both sides by VF. Okay? And so when I do that, I get CF equals CI, which is 14.8 moles per liter, times VI, 0.500 liters, divided by my VF, 1.50 liters. So our liters cancel and we are left with moles per liter for our units of the answer. So 14.8 times 0.5 divided by 1.5 gives us an answer of 4.933 so on moles per liter. And again, if I look back up at the question, I have three sig digs. So I'm going to cut it off after that 3, which won't round anything up, and we'll get 4.93 moles per liter as our, we want to label what that is, our final concentration. Okay, so always read the question very carefully. Look if it's telling you that is the final volume, or if it's being mixed with the initial, then you have to add them together. Okay? And that is it for this video. Thank you very much for watching.